You ever stop to think about the incredible physics that's hiding in, everything around us? The bounce in a pogo stick, the sound from a guitar string, even the little click you feel in a ballpoint pen. Well, there's a single, fundamental rule behind all of them, and today, we're going to pull back the curtain and see exactly what it is. I mean, really, how does a simple spring seem to know how much to stretch or squeeze? How does it always bounce back with such a predictable, reliable force? It kind of feels like magic, but it's actually one of the most elegant and simple principles in all of physics. Okay, think about a bathroom scale. When you step on it, you're not just standing there, you're actually squishing a set of springs inside. The distance they compress is directly tied to your weight, and boom, that's how it spits out a number. Simple as that. Or what about a guitar string? When you tune it, you're just changing the tension, right? You're stretching it. And that stretch, that force, that's what decides the pitch you hear. It's this perfect, delicate dance between pull and resistance. And if you want to take it up a notch, a bungee cord. Its ability to stretch in a predictable way is, and I mean this literally, a lifesaver. It has to soak up all the energy of a fall just right, stretching enough, but not too much. This isn't guesswork, folks. It's pure, calculated science. So what is this secret rule? Well, it's called Hooke's Law, named after the 17th century scientist Robert Hooke. And the beautiful thing about it is its simplicity. So what does that actually mean? In plain English, it just means the more you pull on something like a spring, the more it pulls back at you. If you double the stretch, you get double the force. It's this super clean, direct relationship, and that predictability is exactly what makes it so incredibly useful. And this whole idea is wrapped up in one neat little formula. F equals negative kx. Let's just quickly break that down. F is the force. That's how hard you're pulling. X is the displacement, how far it stretches. Now, K is the fun one. That's the spring constant. I like to think of K as the spring's personality. A really high K means it's a super stiff, stubborn spring. A low K means it's pretty chill, easy to stretch. And that little negative sign, that's just the spring trying to get back to where it started. It's the snap-back force. All right, so a formula is one thing, but how do we actually prove it? How can we see this elegant relationship with our own eyes? Well, turns out it's surprisingly easy to test. You could pretty much do this at home. Just hang a spring, measure it, then add a known weight, say 1 kilogram, and measure how far it stretches. That amount of stretch, that's your X. And since you know the force of gravity on that weight, you've got your F. And just like that, with those two numbers, you can figure out that spring's unique identity, its K value. So let's say after our little experiment, we calculate our spring constant K to be 10 newtons per meter. A newton is just a measure of force. So this number is telling us exactly how stiff our spring is. It's saying, for every meter you want to stretch me, you're going to need to apply 10 newtons of force. It's basically the spring's unique fingerprint. So we've got some data, right? We've added more and more weights, and we have a bunch of forces and the stretches that go with them. So what happens when we throw those points onto a graph? And there it is. This is the beautiful part. You get a perfect straight line. As the force on the up and down axis goes up, the displacement on the side-to-side axis goes up right along with it, in perfect lockstep. This simple, elegant line is the visual proof of Hooke's law. No curves, no weird wobbles, just a direct, proportional relationship. It's awesome. Okay, so this is way more than just a neat experiment for a physics class. The real payoff, the big takeaway here, is that this principle is absolutely everywhere, quietly making our modern world work. Let's look at just how widespread it is. The suspension in your car? Yep, that's using springs designed with Hooke's law to give you a smooth ride. Seismographs use it to measure the force of earthquakes. Even the simple clicker in your ballpoint pen relies on a tiny spring that obeys this exact rule. From clocks to toys to critical medical equipment, this law is the foundation for pretty much anything that needs to reliably push, pull, or bounce back into shape. But, like any great rule, Hooke's law has its limits. There's a breaking point. So what happens when you pull just a little too hard? This is where we get into the difference between what's called elastic and plastic deformation. As long as you're in the elastic zone, the object, like a rubber band you stretch a little, snaps right back to its original shape. Hooke's law is running the show. But if you stretch it too far, you cross a boundary, the elastic limit. Now you're in plastic deformation. Think about a paperclip. Once you bend it, it stays bent. It's been permanently changed. At that point, Hooke's law has left the building. And that is such a powerful idea, right? In science and engineering, knowing the breaking point is just as important as knowing the rule itself. Engineers have to design bridges and buildings that always stay within that elastic limit to make sure they can bend and flex but never, ever break. So, that leaves us with a really fascinating thought to end on. We've seen how useful Hooke's law is for things that need to stretch and return. But the entire field of material science is basically built on asking that next question. What happens at that moment of failure? What can the breaking point itself teach us about creating even stronger, more resilient materials for the future?